merge sort depends on our ability to merge two already sorted lists into one sorted list. This is a pretty simple process, as we'll show here. We start with the first two items in our two different sorted lists, and we simply compare to see which one goes first. In this case, of course, it's Al, and he goes into the first spot in our merged list. We then move on to the first item in each list that we haven't placed yet. So the first list we've moved on to Phil, and the second list we're still at Bob. Compare those two, and clearly, Bob is the next one to go in. We then continue the process with the next item in each list that we haven't placed yet. And so we compare Phil and Jim. Jim's the winner there. And then we move on to John and Phil, where John goes in the next spot. Now notice the second list is exhausted. Nothing left to do there. And Phil is a remaining item in the first list. In general, when we get toward the end of a merge sort, one list will be exhausted, and the other list will have at least one item in it. So the rest of the process is easy. We just basically take all of the items remaining in the one list that has items left and put them in their current order into our merged list. So that completes our merge of 5 items. Notice that it took us 4 tests to complete that merge. Merging itself basically takes on the order of n tests to completely merge a list comprising of a total of n items. Now notice we also did use some extra space. We basically doubled the memory requirements for our sort by creating a temporary place where we could put the new sorted items without having to swap them and move them around. There are other ways to do that, but that's the typical approach we take in a merge sort. Now let's look at some Java code that implements the merge part of a merge sort. We've defined a function here that takes as input 2 arrays of strings that we assume are already sorted, and we're going to return our combined sorted array. First thing we do is create our temporary new array that's the combined length of our 2 input arrays. Then we set up an index into each one of our arrays starting at the beginning. We're using I1 for our first list, I2 for our second input list, and IR, or iResult, for our resulting list. The loop will actually go on until we've exhausted one or the other list. In this case, we're going to get rid of the first list because it's got a smaller length, but it could just as well be the second sublist that had a smaller length. We compare where we're pointing to in our 2 lists, and in this case, the item in the first list is smaller, so we move him into our resulting list. We're using the ++ syntax of Java here on those 2 indices so that as soon as we complete that move, both of those indices are incremented by 1. And that means they essentially move to the next spot in each of those 2 arrays, both the source and the destination array that we just used. We return to the while loop, and we're not done with either array yet. So we move on to the next comparison, and here the second list wins, and so we increment those 2 pointers and move Bob in. Back to the while loop, where we confirm that we're not done with either list yet. So we do the next comparison, and in this case, the second list wins. We move Jim in, and we advance our pointers. Returning to the while loop, confirm that we're not done. Check the next 2 items. List 2 wins again, and we increment our pointers. Now when we return to our while loop, I2 is no longer less than A2.length, because that second list has been exhausted, and this while loop is over. This takes us to the two cleanup while loops at the end. The first of these while loops checks to see if we've exhausted the first list. We haven't, so we take the next item in that first list and move him in. Now we've indeed exhausted the first list, so we move on to our second cleanup while loop that checks to see if the second list has been exhausted. And of course, it already was. And so we take our completely sorted array and return that. So now we have a merge function that we can use in our combined merge sort program. Now that we understand how to merge very efficiently, let's see how to take advantage of that in a sort. So we'll start at the top with our unsorted list, and our mission is to sort Phil, Al, John, Jim, and Bob into alphabetical order. We start by splitting it into two lists. And then we're going to sort each of those two lists independently, and guess what? Merge them back together again. Well, the first sort, oh my goodness, let's do the same thing. Let's sort that list of two and merge them back together again, and then we'll have the first two sorted. There they are, sorted and merged together, and because that merge only took one test, that's all we've used. Now we can go to work on the second part of the list and split it into two pieces. The first one, John, is pretty much clearly sorted already, but we do have to sort Jim and Bob. I've got an idea. Let's split them and merge them. There we are, Bob and Jim merged. Let's merge them with John. There they are. Remember, that only took 2 tests, so we're up to 4 tests total now for our merge sort to date. And our last step is to take Al and Phil and merge them in with John, Jim, and Bob. If you were watching the merge part of the video, you saw this act. That took us 4 tests to do that. So we have managed to sort our entire list by splitting and merging repeatedly, one might even say recursively, for a total of only 8 tests. So for n equals 5, with 5 items in our list, we ended up using 8 tests. If you think about it for a minute, if we doubled the size of that list to 10, well, what's the first thing we'd do? We'd split it into 2 sublists of 5, each of which would take 8 tests, and then to merge them into our final list of 10 would take 9 tests for a total of 25. Continue that process of doubling and you'll see that, the numbers do get a little bit bigger. By the time we've gotten to 80 items in the list, it's going to take us about 433 tests. But let's compare that to the selection sort. Whoa! Not much of an advantage at 5 items, but by the time we're down to n equals 80, we're almost an order of magnitude better with the merge sort. It turns out if you graph them over a large number, you'll find that the selection sort, as we saw before, is order n squared. Basically, as you double the amount of items in your list, the amount of sort time is going to go up by a factor of 4. On the other hand, the merge sort is linear times just the log of the number of items, or n log 2 base n. And look at the difference in how quickly that grows, or really how slowly that grows, compared to our selection sort. That's why for any kind of significant size lists, it's generally worth paying a little bit of a penalty in space to get that incredible speed up in execution time. So let's look at the code that actually implements a merge sort. Thanks to recursion, it's amazingly simple. We're using the same structure for the function that we used for the merge. We pass it an array of strings, and we actually return the sorted array of strings separately. Now, if the array is one item or no items, sorting it's pretty easy. We just give back the original array. That's the base case of the recursion. In the more complicated form, though, we'll of course have more than one item in the array. So we split the array into two pieces, a right and a left. We split it essentially in half, and for an odd number, the smaller number will go in the first and the slightly larger number will go in the second. And then, as we saw in the overview, we begin by sorting the right-hand side first. That's where the recursion happens. We get a second copy of the sort routine now, and it's only looking at those first two items. It's bigger than one still, so we make two copies. And again, we call sort recursively again. This sort is now looking only at fill, an array of length 1, and so it simply returns that array of length 1 back to the previous copy of sort. So in our previous version of sort, the right side is now sorted. And we move on to do the same thing with the left side. Sort is called recursively again. It's still an item of only length 1, and so it's returned back to the previous version, who now knows it's sorted. Two sorted sublists. I'll bet we could merge those. So now we call the merge program that we described before. The merge program creates a new array of 2, merges the two strings into it, and then returns those to the calling sort program. When it returns it to the calling sort program, it's assigned to the same string that we started with, now sorted, and our sort program returns that sorted sublist of 2 back to our original sort. So we've now gone from an unsorted right-hand side of the array to a sorted right-hand side of the array. Now we move on to do the same thing with the left side. We call sort recursively, check the length, create two new arrays representing the right and the left half of the input array, and call sort recursively again on the right-hand array. That one's length 1, so we're done and just return it back. And now call sort on the left-hand side of the array. It's more than one item, so we have to create our two subarrays. Sort the first one, pretty simple. Sort the second one, pretty simple. Merge the two together and return the result back to our calling sort. It now has two sorted subarrays, so it can merge those two together and return back to the original calling sort program. It then does a merge of its two subarrays to create the final sorted array and returns it back to the original caller. There it is, a merge sort, which works much more efficiently than the selection sort or even the insertion sort, and takes full advantage of recursion to keep the code very simple.